And good morning. Today I'm going to start a new series of videos in the form of quiz, and this is quiz number 1. So in this video series I will take 5 basic questions that is purely based on concepts, and we'll try to discuss this. So let's start the first one. The assertion is given to us that the shear stress of a single crystal of steel can be low as 10 meganewton per meter square, while for a sample of 2 micrometer dimension, it can be in the range of 2 into 10 is to 4 meganewton per meter square. So, what is the meaning of this? In the first case here, a stress of a single crystal of steel is very low, but in the second case it is tremendously high. Okay, in the first case we have not given any data about its dimension, but in the second case dimension is very less, that is 2 micrometer dimension. Okay, now let's see the region. The concentration of defects increases when we increase the size. Okay, so this data, the 10 meganewton per meter square, is the low value of shear stress, and this you will get when the single crystal is of very big size. If the size of the single crystal will be big, then what will happen? More number of defects will be there and the strength will be low as 10 meganewton per meter square. But when you decrease the size, then there will be less and less defect, and in this case the magnitude of shear stress will be tremendously high, and that is 2 into 10 is to 4 Newton meter per meganewton per meter square. So basically assertion is true. The first data is for a single crystal of large dimension, but for the second data it is for single crystal of a small dimension, very less, micro, in the range of micrometer. Now the region is also true because when you increase the size, the defects increases. So both assertion and region are true because when we increase the size, more and more defects will be there and the strength will be less. So this is also true. This is also true, and we have correct explanation also. Both are true as well as the correct explanation. Second, carbon nanotube is approximately 100 times stronger than steel, irrespective of the size of the specimen. We have to select it whether it is true or false. So again, we can say that suppose carbon nanotubes is of very small size, like in micrometer, and when it is in big size, like in millimeter or centimeter, then again carbon nanotube, if the size will be more, then more and more defect will be present and the strength will be very low. So again this is not true because always carbon nanotube is not going to be more stronger than a steel. That is not true. It depends on the size. If the carbon nanotube will be in the range of nanometer, then it will be stronger than a steel. But if it will be in the range of millimeter, centimeter, then it will be very weak in strength and less stronger than steel. So this statement again is false. Third is single crystal is free of any defects. So this statement is again false because single crystal can have the defects like we can have dislocations, vacancies. These are the equilibrium defects, so we can't get rid of these defects. Thermodynamically, we can't get rid of these. So these defects will be present there in the single crystal also. And that's the why when you increase the size of the single crystal, defect will be more and strength will be less. So single crystal will be of very high strength provided its size should be small. Now we have to match with the following: allotrope of iron, crystal structure, temperature and pressure. So let's see. We have alpha iron, that is also called ferrite. Alpha iron is the BCC form, so this is going to match with the BCC form, and it is stable up to 9010 degrees centigrade from room temperature to this, so it is matching with that. Similarly, we can have gamma iron. Gamma iron is called austenite, that is austenite, and the gamma iron is FCC crystal structure. And gamma iron, when you solidify iron, then gamma iron start forming when the temperature goes below 1394 degrees centigrade. So it will match with this one. Next is delta iron, that is BCC again, BCC crystal structure. And when you solidify iron from its melting temperature, the first phase that is going to form is the delta iron, that is temperature below 1538 degrees centigrade. And the last one is the epsilon iron, and it is basically a HCP crystal structure, that is the hexagonal close packed, and this is not stable at room temperature, or this is stable only at very high temperature, like in the core of the earth. Temperature is very high, that is around 6000 degrees centigrade, and very high pressure. So these are the various match. The last one is, let's see this one. Melting point of iron is fixed irrespective of its size, and this is again false, because we know that when you decrease the size, surface area increases. When surface area increases, then surface energy increases. Surface energy, that the total energy for the particle that increases, and due to that melting point decreases. So we can't say that melting point of iron is fixed irrespective of its size. When iron is of very small size, like 5 nanometer diameter, this much size, then its melting point will be very low, and it may melt at around 500 degrees centigrade only. Because of the small size, the surface area will be high surface energy, so more number of broken bonds, so melting point will be very low. That is, iron can melt up to 500 only. So these are the 5 basic questions. So we'll continue it. Thank you.